Welcome to Positive Physics. Today we're looking at evaporation. So have a look at my little diagram here. In a liquid, the particles have a range of energies. So some of them are moving very quickly, some of them are moving more slowly, even if the liquid is at one temperature. Some of those particles that are at the surface, the ones with the most energy, have enough energy to escape from the surface and go into the air. They have evaporated. They've left the liquid and become a vapour. What that means is that the particles that are left in the liquid here have less overall energy. And when something has less energy, it will seem cooler. Here, our particles have a range of kinetic energies, that's how fast they're moving, and the average kinetic energy is linked to the temperature. The average kinetic energy, once these faster particles have left the liquid, will be lower, and so the temperature is lower. Now, what that means is that wherever our liquid is, it's probably now cooler than our surroundings, and so it can absorb heat energy from the surroundings, or there will be a flow of heat energy from the surroundings, in this case through conduction of the walls into that liquid. And what then happens is that those particles will gain kinetic energy again, and the ones near the surface with the most energy can escape, and the process repeats, absorbing or taking in energy from the outside surroundings, particles gaining kinetic energy, and the ones near the surface escaping and taking that energy with them. Now, if we were to do a little experiment and to take two identical bottles and fill them with the same volume of water at the same temperature. So here I've got a bottle with 100 centimetres cubed of hot water at 70 degrees centigrade, and I've got the same in this bottle here. I've got the same starting temperature and the same volume, and I've got, importantly, the same surface area on the outside of my bottle. Now the surface in this instance is where the heat transfer is going to take place to the surroundings. So as this water cools, it's going to conduct through the walls of the bottle, and then it will be passed into the surrounding air. I've added a lid to both of them, or a bung, and that's to stop convection, where the air above the top of the liquid is being heated by the water in the liquid, and then we have a convection current where the hot air will rise up and leave with its energy out of the bottle. The bung stops that happening. It keeps the hot water vapour inside the bottle. Now what I've done here is I've put wet paper towels around the outside of one and not on the other. And what do you think we'd see if we actually did this experiment? Well, actually, what we would see is both of the bottles would lose thermal energy and the temperature would decrease. But the one with the wet paper towels on, the temperature will decrease much more rapidly. And that is because the water in the wet paper towel is being heated up by the water, the thermal energy inside the water in the bottle, transferring to the wet paper towel. The water molecules in that wet paper towel gaining energy and therefore evaporating, leaving the liquid in the towel and taking that energy with them. So we've got an extra mechanism to remove thermal energy from our water here by having a wet paper towel on the surface. And this is why on a really hot day you might see some sportsmen put a wet towel around their neck, and you can buy these ice towels now, but actually you can have the same effect with an ordinary towel and water. If you put water in it and put it over yourself, you will cool down. It's why after marathons the athletes cover themselves in that silver blanket. Firstly, to prevent radiation of infrared thermal energy from their bodies. Secondly, to prevent convection of the air being heated around their bodies and that energy being leaving. And thirdly, to prevent the sweat on their skin from evaporating and taking away that thermal energy by leaving that water close to the surface. Now, there's one thing you need to be really clear about when it comes to evaporation, and that is that evaporation is not boiling. So here we have evaporation. Evaporation only happens on the surface of the water or the liquid, and it happens at any temperature. So a puddle will evaporate. If you put some water in a glass outside at 20 degrees, it will over time evaporate. Boiling happens everywhere in the liquid, and you can tell that because you can see those bubbles forming everywhere in the liquid. And it only happens at the boiling point. And so for water, that's 100 degrees centigrade. So evaporation only at the surface, those fastest particles having enough energy to escape the surface and leave and taking their energy with them, so the liquid cools down. Boiling happens everywhere because lots of the particles have enough energy to escape, and you get these bubbles forming where they're producing vapour within the liquid. So there we go, evaporation, how it can help you cool things down more quickly, and why it's important to know the difference between evaporation and boiling.